Are we in a new space race? Why is NASA so slow? Does dark energy only happen in empty space? And what happens if you feed more material to a neutron star? All this and more in this week's Question Show. It's time for the Question Show. Your questions, my answers, as always, wherever you are across my channel. If a question pops into your brain, just write it down. I will gather them up and I'll answer them here. And just a reminder, we do the show live every Monday at 5 p.m. Pacific time. So if you want to come and ask your questions live, watch my reaction, listen to other people in the chat who will expand upon your question to make it even tougher, come join the live show. There should be a live event somewhere here on the channel. I'll tell you when the next one is going to be. But if you really want to know for sure, make sure you're subscribed and then make sure you click on the notification bell and then you'll get an email when we're about to do the live show. Of course, it will probably arrive late and then you'll be wondering what happened. But also that's a permanent link to the episode in case perhaps we make it unlisted after we do the live show. So, all right, let's get into the questions. Jim Krause, 1975. Is dark energy in empty space only? How does some space know to expand while other space knows not to? Or so it seems, right? So dark energy is this mysterious accelerating force that is increasing the expansion rate of the universe. And astronomers discovered it totally by accident. They were trying to measure how the universe was slowing down in its expansion after the Big Bang. And so they looked at an object called a Type 1a supernova, which always explode with the same amount of energy. And so when you see one, you measure how bright it is, and then that tells you how far away it is. And they were measuring these Type 1a supernova, and they were trying to sort of find out again how, like, if the universe was going to coast to a stop. And they didn't find that. They actually found that the expansion of the universe was accelerating. And they didn't have a name for this, so they called it dark energy. And I know you don't like the name, but that's the name we're stuck with. Feel free to suggest a better name. But one name that actually had been proposed decades before is the cosmological constant. And so when you think about the universe and you think about all of the matter and all of the energy and all of the stuff that's going on inside the universe, and Einstein sort of thought about this and he said, well, if you took away all that stuff, you would just be left with the vacuum of space. But it's not nothing, it's something. It's space-time. And he figured that if you were to have a universe that had been around for at some point in time, it would either be expanding or contracting. Like, it would be super weird for it to be perfectly balanced. And yet, as astronomers discovered that the universe seemed pretty balanced, he figured, okay, well then this cosmological constant that he had to put in, sort of like a fudge, wasn't going to be necessary. But then later on, astronomers, as they were actually measuring this expansion rate of the universe, they found, yes, indeed, that this sort of intrinsic nature of space itself would be the cause of this expansion. And sort of the current estimates for how much energy density there is from dark energy is 7 times 10 to the minus 30 grams per cubic centimeter. And just to like give you a comparison, like water is 1 gram per cubic centimeter. A liter weighs a kilogram. And so dark energy is producing just a phenomenally low amount of energy, and yet space is really big. And so the more space that you get, the more dark energy that you get, and that expands space more, and then you get more space, and that gives you dark energy. And so you're wondering, like how does space know where the dark energy should be and where it shouldn't be? And the answer is that it's everywhere. That for every cubic meter of space, there is a set amount of dark energy that appears in that cubic meter of space. And it doesn't matter if that cubic meter of space is inside a planet or inside a black hole or inside the emptiest vacuum you can find in the universe. It's just that the force, the outward force that's coming from dark energy is so low that it can't overcome the gravitational force that is holding the planet together. It can't overcome the atomic force that's holding your body together. It can't even overcome the gravitational force that is pulling Andromeda towards the Milky Way, or the gravitational force that's holding all of the galaxies in our neighborhood. It's only at larger scales, when you get to the tens of millions of light years, that now there's enough dark energy between the Milky Way and another galaxy that is tens of millions of light years away that in fact it is the dark matter that is the dominant force. And so even though that galaxy would really like to collide with us in the future, dark energy is pushing it away. And that is going to be continuing to accelerate until all of the galaxies that we can see today at the farthest edges will just fall over the cosmological horizon and fade away from our perspective. So from what we know right now, dark energy is sort of equally present at every place in the universe. I'm sure you've noticed the Star Trek planet name that's appeared above my shoulder, and this is a way for you to vote for which you thought was the best question answer asked this week. So I will, as I go through the questions, a different planet name will remain in the upper corner for the entire question. These come from the Star Trek universe, so they're good names. So just watch the end of the episode and then put in the comments the planet name that you thought was the best. And so last week, the winner was the SPAS AZ. JWST and other telescopes have provided examples of gravitationally lensing and resulting smeared images of a distant object. Could you reconstruct the original image? And of course, we answered that question in depth. So thank you for asking the question. And I'm glad you guys enjoyed the question and the answer. Go ahead and put your vote for this week's question into the comments down below. Istvan Suppose 9940. I thought it was also the American pronunciation for lava and pasta, and then Google confirmed it. Or I just don't hear some tiny little difference. Or is there a difference between the US and the Canadian pronunciations of those words? So in the last episode, I was going to go and do a big long conversation about lava tubes, but I needed to prepare some of you in the audience to listen to my Canadian accent. And yes, it is different. Now, for people who maybe aren't American or Canadian, you might not catch the difference. So an American would say pasta. So like, oh, would you like a bowl of pasta? Yes, I would like a bowl of pasta. Let's eat this pasta in my Mazda, on the llama, and in this lava tube. And I would say, would you like a bowl of pasta on the llama, in the Mazda, oops, in the lava tube? And so I think that Canadians, because we sound so similar to Americans, because I get like a lot of people going like, you Americans, blah, blah, blah. And I'm like, I'm not American, right? Different country. I think we sound so similar to Americans that it's the differences that are like the uncanny valley. Like it's too weird. And most of the time you can't tell the difference between us. And every now and then we'll say something. And the one that my wife thinks is hilarious is the way I say resources with it like Z. And she's like, you don't have sources, so why do you have resources? I'm like, I don't know. Like, that's just how we say it. And one kind of tell is if you're watching a TV show and you hear an actor say resources, while an American would say resources, which sounds really alien to me. But yeah, so I know you're waiting to hear me say a boot, and I don't say that. I say about. It's definitely different than the way an American says it, but it is kind of subtly different. And it's definitely not the a boot. Although, there are plenty of Canadians with different accents. People on the East Coast are different from people on the West Coast where I live, different from people in the middle of the country. It's a big country. But anyway, there you go. That's what you should be listening for when I say lava. Ian Botha, 9912. Talking about a neutron star at the center of a nebula, what would happen if the nebula collapsed back onto the neutron star? When you have a star that is many times the mass of the sun, it is able to burn more complicated fuels up the periodic table of elements inside of it. Our sun, once it hits like carbon burning, it's done. It can't do any more. But the heavier stars, they can keep going up to carbon. They can go from carbon, they can go neon, they can go all the way up. And when they reach iron, they can't get any energy out of the fusion. So they're no longer producing radiation pressure, and all of the mass of the star then can collapse down in. And that gets you the supernova. Often you get like a neutron star or a black hole if it's more massive than that. And then you get the supernova explosion as sort of like this bounce off of this compact object in the middle. And so now you're left with the neutron star. And it is like the size of a city. And yet it has twice the mass of the sun in it. But it's not a black hole. Like, it still shines with radiation. You can still see it. Now, you were asking about the nebula. Like, why doesn't the nebula sort of get pulled back into the neutron star? And that's because the nebula is the explosion that is coming away from the neutron star, and it is going so fast, it is just gone. And one of my favorite images is this supernova 1987A, which was seen in the Large Magellanic Cloud. It's like 165,000 light years away, and you can see this ring. It looks like when the Death Star blew up, and this ring of material is moving away, and that will turn into a larger, more diffuse nebula over thousands of years. We see examples of this, like the Veil Nebula, which is part of the Cygnus Loop. It's this gigantic structure, and this is just like the blast of the supernova. So it's not coming back. It just has too much velocity, and it's gone. But what if it did? Or what if a neutron star found a new source of fuel? And this is still a bit of a mystery. Like, you have a white dwarf. And if a white dwarf reaches 1.4 times the mass of the sun because it's feeding on some companion, then it turns into a supernova. It explodes. And you get that type 1a supernova that I talked about earlier on. And it's just completely gone. But what happens to a neutron star as it is continuing to accrete material from some partner? Does it reach some point where it collapses one more stage? And so astronomers have proposed that there's another kind of neutron star called a quark star. And that would be where now, like, all of the neutrons in the neutron star are compressed down. And so now it's just this soup of quarks. And then maybe as it continues to gather more material, then it finally collapses into a black hole. And it's so dense that it then sort of takes that next step, disappears, and now is absorbing all of its own radiation. And so this is still a bit of an unsolved mystery in astronomy that we don't know. And so if a neutron star can feed on some source of material for long enough, what happens? Does it explode? Does it collapse one more stage and turn into a black hole, but also explode? And you're left with a black hole? We don't know. And it's a bit of a mystery. Whitcode, has there been much thought in using a data hauling satellite on a cycler orbit for high bandwidth data transfer? It seems that would be nice for an extreme long baseline interferometry telescope. All right, you are definitely a fan of the channel that you are sort of going this deep into the problem. So we talk about this idea of putting powerful telescopes far away from the Earth. Like, wouldn't it be cool if we built a gigantic interferometer where we sent one telescope to the Earth-Sun L4 point, the Earth-Sun L5 point, and one to the L3, and now you've got a triangle where the arms are 200 million kilometers long. That is a big telescope, and it would be amazing what you could see with that kind of resolution. But the problem is that the L4 and the L5 points are very far away, much farther away than the L2 point. And so you would have decreased bandwidth being able to send that information back to Earth. And like, I think when a lot of people think about these ideas, they hand wave them away and they go, well, bandwidth schmandwidth, I don't care, right? Well, no. When you build an interferometer, it is all about recording as much data as humanly possible using atomic clocks with really gigantic storage systems. And then you mash this data together with supercomputers to pull out the interferometry. When we think about some of the communication systems that are out there in space, like for example, New Horizons, when it flew past Pluto and it took images for a couple of days of Pluto and Charon, it then took 18 months to get that data back home. In some cases, it was sending data home in dozens of bits per second, and it's probably even less now. When we saw these new pictures from the Lucy mission, when it did its flyby of Dinkinish? Anyway, I should learn the name of this. We had a delay in when the data came back to Earth, and that was because the spacecraft is so far away and was only able to transmit data for such a slow amount of speed that it took a while to get the data. And we still haven't got all the pictures yet. And we are a week after the flyby, and it's going to probably be a few more weeks before we finally see all of the pictures at the highest resolution that the camera was able to capture. So what if we came up with some kind of physical solution? Now, there is a mission that kind of does what you're talking about, and that is TESS, the Transiting Exoplanet Survey Satellite. And this is the spacecraft that is searching for planets that are close to Earth, orbiting around stars, and they're blocking the view from the star occasionally, and we get this blink on the stars. And TESS is on this really interesting orbit that carries it relatively close to Earth and then fairly far away in this way that sort of interacts between the Earth and the moon, and it sort of is kept stable in this long orbit. And so it does this flyby, and it's like, I think it's like a month that it flies out, gathers all of its data, and then at its closest point transmits all of its data and then flies back out. And I think you're on the right track that for missions that are going to require like a lot of data to be gathered up, but then also to be able to transmit that data back to Earth, then we're going to need to come up with some clever idea. And maybe the spacecraft itself does this, or maybe, as you say, there's like a data cycler satellite that's only job is to fly close to various missions that are gathering tons of data, quickly transmit all of the data when the two satellites are very close, and then bring that home to Earth, and like maybe even deliver physical devices. That maybe it drops hard drives back down through the atmosphere of Earth because there's that much data that needs to be gathered. But even if it does a close flyby of Earth within a few hundred kilometers, is able to transmit all of that data and then back out to space to pick up more data. Yeah, I think there's possible. I mean, the more infrastructure that we get in space, the more large transmitters at various orbits that are able to collect data, be able to send the stuff back to Earth, then the better everything is going to get. But we're still at this point where every spacecraft that we send out into the solar system has to be completely self-reliant. And you'll know that things are really starting to change once we start to have that infrastructure around other worlds, and we're just not there yet. Juan Mendez, are we officially in a new space race? What are the key goals? Who are the competitors? Who is ahead? I don't think we are officially in a new space race, but we are unofficially absolutely in a new space race. So there are a few competitors to think about. So the first one is NASA itself. And of course, they've got the Artemis mission. We've seen Artemis 1 launch. Artemis 2 is due to launch sometime in 2025. And then Artemis 3 is going to launch in 2026. But, don't be surprised if it gets delayed. Artemis 3 is the one that's going to have humans return to the moon. And they're going to be using a SpaceX Starship, the human landing system that will actually carry them from lunar orbit down to the surface of the moon and then back up into the Starship. And that sort of tells you who the next part of the race, the new moon race, and that is SpaceX. SpaceX, one of their plans with the SpaceX Starship is to do human flybys around the moon and probably to send commercial missions to the surface of the moon. Like if they can demonstrate that they can land this thing for NASA, then they'll demonstrate that they can land this thing for other paying customers. So you've got both NASA with SpaceX, but also SpaceX on its own. And then you've got sort of other collaborations. You've got Blue Origin and other companies that are working together, both in terms of sending humans to the moon, as well as sending like commercial packages like astrobotics and things like that. And so I think over the next 10 years, you're going to see a dozen companies step up and try to work out how they can send commercial packages. There's a Japanese company that is going to try this as well. So I think we're going to see a lot of commercial missions going to the moon, not carrying people, but definitely carrying telescopes and cargo and rovers and things like that. And then, of course, the other big competitor for this is China. China has said they're going to land humans on the moon before the end of the decade. So before 2030, probably 2029 is their plan. And I believe them. They are working on their new version of the crew capsule. They're working on their new version of their heavy lift rocket. They are going to do something very similar to what NASA is going to do. They're going to essentially put the crew in one crew capsule and launch them on this super heavy lift rocket. And then a second super heavy lift rocket is going to take the lunar lander, and both will go out to the moon. And then the astronauts will get out of the capsule into the lunar lander, and then they'll land on the moon and then come back up to orbit, get back into their capsule, and then come back to Earth. And they are laying all the groundwork. When you think about the missions that the Chinese have done, they've done landings on the moon. They've done sample return missions from the moon. Their next set of missions is going to be, I think, another sample return mission from the moon. And then they're going to do some in situ resource utilization missions to the moon, where they're going to try to extract resources out of the lunar regolith itself. And this should all culminate in 2029 with their first humans setting foot on the moon. Obviously things could be delayed, but that's the plan. And so far, I mean, they're hitting all of their milestones. And so don't be surprised. And then of course, India is building its own human systems. They're planning on building their own space station. They're planning to send people to the moon, and they say they're going to be able to land by 2040. And again, I think, they have a very dynamic space exploration program. They sent a mission to Mars. They've sent a lander to the moon. They just sent a space telescope to the sun. So they've got a lot of really interesting missions. And so if they can crack sending people into orbit to a space station and then figure out how to send people to the moon. And so I think how this is all going to play out is we'll probably see NASA land on the moon in 2027. If SpaceX is able to provide the human landing system, then I think we'll see some number of SpaceX landings between 2027 and the end of the decade. And then we will see the Chinese land in 2029. And then begins the Mars race. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Do you want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to the recent newcomers: Chris Foran, Bernard Kozoil, Creighton E. Wood, Chel Baker, Dean Penner, Jeff P., Richard Laub, Tom Mason, Carrie Karchner, and Analog 2. Join the club at patreon.com/universetoday. Creighton Daniels: how come NASA is so slow? Why not several rovers on the moon, AI or not? Well, this is the eternal question. And welcome to the club, where we wonder why this whole space exploration thing is taking so long. And for you, asking this question today, you've got SpaceX with Starship trying to build the first fully reusable 2-stage rocket. We've got lots of other competitors in the space launch races. You've got SLS, we've got what the Chinese are doing. There's a lot of interesting things that are happening right now, and yet it still just takes an agonizingly slow time, doesn't it? Well, that's just space. Space is hard. It's called rocket science for a reason. And it is chronically underfunded for the complexity of the goals that Congress and other leaders give to the poor people at NASA to try and accomplish. We know that the space launch system in its current state is underfunded for the goals that they're given. In other words, it's going to probably cost $2 to $4 billion per SLS to launch forever. And yet NASA doesn't have $2 to $4 billion provided to them to launch SLS rockets. And so they've got a certain amount of runway right now. They've got a certain amount of resources that they can bring to the table, but eventually they're going to run out. And so either Congress is going to have to raise the amount of money that NASA gets, or NASA's going to have to change their tactics or not go to the moon. And so it is always this problem that space exploration, although exciting, and you love it, I love it, everyone watching this channel loves it, but most people don't see it as big a priority as a lot of the other ways that they want to spend money on. And you can't easily make space a lot cheaper. Even SpaceX has been able to dramatically drop the costs of rocket launches. When you think about the price of launching on a Falcon 9, on a Falcon Heavy, theoretically Starship, but even Starship is starting to consume gigantic budgets because it's so complex, so expensive, and hopefully it'll be game changing when it actually happens, but it is not coming cheap. And so it's just that on the one hand, people have goals. When you think about the solar system and you think about the moon and Mars and asteroids and Titan and all of these places that you want to visit, and there's just a set amount of budget, it just doesn't go very far. And you just have to be patient. You just, like many of us, you just have to realize these things take longer than you were led to believe, that you had hoped. Clinton Knox had this thought during your interview with Dr. Adam Frank: could the Boötes void or any other void actually be an area with a civilization that has built Dyson spheres everywhere they have reached. I like that idea, but no. And the reason is just because Dyson spheres will give off infrared radiation. There is no free lunch. You cannot break the laws of thermodynamics. And so if you enclose your star in a sphere of some variety, and like it's not a sphere, like I know it's not just a sphere because that's not stable. So imagine a swarm of satellites, all of which are blocking all of the light that is coming from the sun. And so each one of them is going to be intercepting photons, and it's going to be doing work. It's going to be computing or calculating crypto or whatever. But then these satellites have to emit radiation. And so they're going to be emitting infrared radiation. And now you're saying, well, why don't they just put another sphere around that? Okay, fine. But then that one is going to have to emit infrared radiation that if you try to fully enclose your star and you don't let the radiation out, you have made an oven, and you will eventually make the inside of your sphere an infinite temperature. Like, I don't know what kinds of elements, what kinds of materials can handle being millions of degrees hot, but it is not many. So eventually you have to let that heat out into space, and it will give off this very strong infrared signature. And so if you've turned all of the stars in your galaxy into Dyson spheres, then you're going to have a galaxy that just looks like it's in the infrared. It's going to look like a galaxy, like imagine Andromeda, but yet it's all just bright in the infrared and you don't see all of the visible stars. And the crazy part is that astronomers have actually looked for this. They've actually done surveys of the sky looking for these anomalous infrared galaxies that would be the existence of a type 3 civilization. And so far they haven't found any. It doesn't mean they're not out there, but so far any survey of space for both Dyson spheres inside the Milky Way as well as type 3 civilizations outside of the Milky Way have not turned up anything. So nope, you cannot close up your star and not release the heat unless you violate the laws of physics. And then if your answer is, well, what if they know how to violate the laws of physics as we understand them? Then the answer is absolutely they can. You bet. Disseros, autism, and ambient. What is the upper limit of the mass of a star where it would not go supernova? What would happen? So the smallest possible star, the least massive star that will go supernova, a type 2 supernova, the one I talked about earlier on in the episode where you've got all of the outer layers that collapse inward, is about 8 times the mass of the sun. And so when a star that has more than 8 times the mass of the sun dies, it forms a neutron star. And that the upper bound on that is about 15 times the mass of the sun. So between 8 and 15 times the mass of the sun, then you get a neutron star. If it's above 15, then you get a black hole as the outcome. And then you're left with an object that is like 2 to 3 times the mass of the sun. That's the mass of the neutron star. Below that, in other words, below the 8 times the mass of the sun, you get a white dwarf, just like the kind of star our sun is going to form. Now you'll get a different kind of white dwarf because it was able to burn heavier elements in the core. And so maybe it's not going to be carbon, it's going to be a mixture of neon and I don't know the chemicals that will be in exactly, but it'll be heavier than and more dense than the white dwarf that our sun forms. But you still can't have a white dwarf that is more than 1.4 times the mass of the sun. That gets to a supernova. And so you've got, the star is going to puff out all of this outer layers of its material. It's called mass loss. And so the star starts out maybe it's 7 times the mass of the sun. And then it starts to run out of fuel in the core, and then it starts to blow it up as a red giant, and then it shrinks back down again and switches to a different kind of burning in its core, but now that outer layer is now drifting away from the star. And now it maybe only has 5 times the mass of the sun. And then it bloats up as a red giant again, and then contracts back down, and now another shell is making its way out into the universe. And it'll do that so that it can end up being less than that 1.4 times the mass of the sun. But then later on, when it does turn into a white dwarf, it can feed on additional material and then detonate as a supernova if it's able to find a source of food. George Badams, do we currently have any protections in place against solar flares that might disrupt our power grid or satellites? No. We don't really have any proper protection in place. So where we stand right now today, if the sun threw a really powerful solar flare at the Earth, it would be a very bad day. you would get satellites failing in space. You would get giant power surges flowing through connected energy grids. You would have transformers going down. You would have big chunks of our electrical grid going down on the side of the world that was facing the sun. It would be a very bad day. And the kind of world that we need to build to be able to handle this first is one that has a very good warning system. And this is something that astronomers are trying to work out right now today, which is that they watch the sun from various different perspectives, and they have these big machine learning algorithms that they're running that are telling them, if you see this kind of activity on the sun, this is more likely to lead to a big flare. Or they see some kind of coronal mass ejection off the surface of the sun, and they know that that's going to turn into the kind of flare that's going to cause problems for Earth. And they're getting to the point now where they have like an hour warning. Woohoo! That's great. So now, if we get this really killer solar flare, we'll get a little bit of a warning, which is great. Good news for everybody. And hopefully you can increase that where you get a couple hours warning. And folks like NOAA in the United States and in other countries are starting to build warning systems. Like here on Vancouver Island, where I live, we have a tsunami warning network. And so if you're on the beach and a potential tsunami is coming in, there's alarms that go all up and down the coastline to say, get off the beach, get to higher ground. And so you will probably have some kind of warning system on your phone that will tell you that a powerful solar storm is inbound and you should unplug your toaster, unplug your computer. The thing is that you just don't want to leave your devices connected when these power surges can move through the system. You want each thing to be isolated, and that will minimize the damage that you're going to do. But I know you can't unplug your house from the grid. Like, you're kind of stuck there. And so the next stage of this is to actually to build a more distributed power system where you're not going to get these giant charges, where you've got people who are, say, using solar power or wind power, and you've got smaller clusters of connected power, so that you could get like one small cell taken out, but the rest are going to be fine, and then they could switch over and transfer power around. But it's going to require like a complete revision of the way our electrical grids work from what we have today. And like, it fits naturally with renewable energy, with solar power, wind power, things like that. And so I wouldn't be surprised if we get to this future where we do have a more local power system that is also a little more resistant to solar flares. But we are not there yet. So right now, I mean, I've heard estimates that a really bad solar flare is like $1 trillion disaster. And you don't have to sort of run your imagination too long about, like, what if the power went down for North America for a month? Like, is that recoverable? Like, it would be really bad. So no, unfortunately, there really isn't a comprehensive strategy to deal with it yet. Super Guppy, when it comes to science discovery, are there any topics that you find controversial? That's a really tricky question for me, because all I do is sort of synthesize scientific discovery. And as a science journalist, our default way of describing things is to use a lot of weasel words. So we'll use maybe, can, might, could, should, would, if, like a lot of that. Like every title that I come up with for Universe Today is astronomers might have found a blah, blah, blah. And if you ever dare not use that kind of uncertainty in your language, then you'll get a sternly written letter from somebody saying that you are doing a bad job of communicating the state of scientific discovery. And so by default, everything that I look at and everything that I think about is controversial to some degree, because it is news. And generally, like, if a thing is controversial, that helps make it newsworthy. If it is newsworthy, it's probably controversial. Obviously, here's some cool new pictures of Ganymede taken by Juno. That's not controversial, so I don't have to use it. This is a new picture of Ganymede taken by Juno. I don't have to use any weasel words. This might be a new picture of Ganymede, maybe taken by Juno. We don't know. We're not sure. Results aren't in yet. But for the other kinds of stuff where someone is making a hypothesis, they've got a 3 sigma discovery, 3 sigmas of evidence for what they're looking for, we are firmly in, you know, a certain amount of uncertainty, and that just goes with the territory. And so I can't even think in any other way. It's weird, right? Now, there are theories that I love. Like I would really like dark matter to turn out to be primordial black holes. Like I just think that's cool, that there are these very low mass or very large mass black holes wandering the universe, and that's what we can't see. That's a crazy cool idea. But there's no reason to believe that's the correct answer, and there's, you know, it's very hard to prove. So no. And like I wonder if this is just me, or I wonder if this is when a person has a properly trained skeptical mindset about scientific discovery. Like this is where you get to, where you kind of think like everything is provisional. Whenever anybody tells me anything, I go like, what's your evidence? You know, how many sigma are you saying? And I don't get very emotionally invested into any one theory. You know, I was having an argument with somebody in the YouTube comments, which is always very productive. And they were saying that, you know, you're just so close-minded. You can't see that there's aliens everywhere. And I say like, I'm open-minded. Like I want to be wrong. I really want to be wrong. I can't wait for somebody to deliver evidence to me that shows me that there are aliens visiting Earth and that we are not alone in the universe. That would be the greatest day of my life. And I just don't see any evidence yet. And so I just have to wait for more evidence. And it is really weird to me when I see people get upset in the YouTube comments about scientific topics that I think are in the middle of the scientific process, that people are doing a good job of trying to get to the bottom of what is dark matter, what is dark energy, what are the effects of climate change on Earth, and all these kinds of things, right? Like, why get upset? Like, why not let scientists who have spent their lives working on this, studying this, continue to work on these mysteries and tell you what they found? And if you think that they're not doing a good job, then by all means, go and take the classes, go to school, catch up to the point that you can replicate the science results. And if you overturn them, good job, you did it, right? But to sort of argue in the YouTube comments or to have an emotional reaction to things is so bizarre to me. So, like, you broke my brain. I can't think of topics that I find controversial. Everything is exactly as versatile as it should be. Alan Snyder, what is the latest news about life on Europa? There is no latest news. Right now there is NASA's Juno mission, which has explored Ganymede and is now currently exploring Io, and hopefully we'll do some more flybys of Europa. But you know, the hope is that we can see some geysers coming out of Europa. There's tentative evidence that there are geysers, not like what's happening with Enceladus, where there's mountains of evidence of geysers coming out of Enceladus. Like, just tentative evidence there might be geysers in Europa, and if there are, then maybe we can fly through them. But we're going to get a lot of answers when NASA's Europa Clipper mission gets to Europa, and its only job is to study Europa, to try and figure out, are there organic molecules on the surface? Does it have geysers? How deep is its water ocean? Are there chambers underneath the surface where things are shifting around and maybe water ice is making its way from the bottom of the ice layer up to the top? That would be really great. So we got to wait for the Europa Clipper, but it's a very powerful question answering machine that's going to be on its way to Europa very soon now. All right, those are all the questions that we had today. Thank you, everyone who asked questions in the YouTube comments, as well as everybody who showed up for the live show. It's a lot of fun. I look forward to this every week. Now, remember, we do this show live every Monday at 5 p.m. Pacific time. So subscribe to the channel, click on the notification bell, and then you will get a reminder when we're about to do the live show. And that way you can show up live. All right, I'm going to talk about some media that I like again this week, but first, I'd like to thank our patrons. Thanks to David Richards, Mark Anstis, Joel Yancey, Antonio Lofilar, Dustin Cable, Vlad Shiplin, Modso, George, David Giltonad, Andrew Gross, Jeremy Mattern, Josh Schultz, and Jordan Young, who support us at the Master of the Universe level, and all of our other supporters on Patreon. So back to another video game that I love, and last time I talked about how much I love RimWorld, and still, like, after enthusiastically praising RimWorld, I then began playing another game of RimWorld, and it's such a good game. But the other game that I really like is Stellaris, and if you're a fan of like strategy games, like Galactic Civilizations, or was it Master of Orion? There are all these like games where you start off as like one civilization and then you explore your nearby space and you're like setting up new colonies, you're building a larger fleet, you're meeting other aliens and you're having diplomacy with them. Stellaris is the game for you. And they do a really good job of making the game as simple or as complicated as you want. So if you want to just press buttons and have new fleets show up off the line, no problem. But if you want to get in and fine tune every single part of your spaceship, you can totally do that as well. And so you can change your fleets so that they're better to match the kinds of weapon systems that your enemies are using. The diplomacy is very complicated. Like the number of buttons you can press is overwhelming, but you can sort of take it bit by bit. And they also do a really good job in this game of having interesting story events. So there are like early story events that give you special bonuses and rewards. And there's like middle story events where you're starting to deal with threats from some of the other alien sort of fleets around you. And then there's these end game sort of existential threats that if you haven't gotten yourself to a certain place, you're going to be wiped out of the galaxy. And I love every part of Stellaris. It is a comeback and I will play that game again and again and again. So if you're looking for a really great, very complicated, but not too complicated space game, I highly recommend Stellaris. All right, we'll see you next week.